factor. So I'm going to clear this off, and I'm going to show you how to proceed by factoring. So we factored now, and now we need to go about solving for the values of x that ensure that this factorization holds. Well, what we do is we essentially have a multiplicative, and we know that only one of these needs to be 0, but as long as one of either x plus 3 or x plus minus 1 is 0, we're going to get 0. So we can first look at x plus 3 equals 0. Note that when x plus 3 equals 0, x is going to be minus 3. We can also look at x minus 1 equals 0, and that's true when x equals 1. So we've found our roots, and they're the same as the ones that we found using the quadratic formula. And that is shown down here as well. So you can always use the quadratic formula, and you'll get the same answer. Turning to b, we have a problem, x squared minus x equals 1. So you can't actually factor this. You can go ahead and try, but it's not possible to come up with a common factor for this. And when it's not obvious and not possible, you can always, of course, just go straight to the quadratic formula as we did before. In this case, our b is going to be negative 1. Our a, again, is 1, and our c is also negative 1. So here's negative b. Here's b squared. 4ac all over 2a, which is just 1. Inside of the radical and the discriminant, we have 1 plus 4 is 5, so we have square root of 5. 1 plus or minus square root of 5 over 2, and this is a sufficient answer. You don't need to type it in your calculator and compute the square root of 5 and write down an irrational number decimal point. That is not necessary. This is the answer. This is actually a more exact answer than if you were to compute 1 plus square root of 5 divided by 2 and 1 minus square root of 5 divided by 2. And that is because the square root of 5 is an irrational number. So the square root of 5 is actually 2.236 ... going on and on and on. So square root of 5 is approximately 2.236067977499979 ... going on and on and on. You're never going to be able to write all of these digits, so it's better and actually more exact for you to just leave it in this analytical form with the radical here. This is a more exact and more analytically correct answer. So again, unless you're asked to round your answer to the nearest decimal, do not, for anything like this, ever go about actually taking the time to put the square root of 5 in your calculator and solve this down so that you don't have any type of radical expressions in it. This is fine as is. In fact, it's better. So that's one thing I wanted to note with this particular problem. Okay, I'm going to clear this off. Moving on now. We have one more example to do with quadratics. We have the square root of the quantity x squared plus 4x equals 0. Now, this is an interesting problem because it doesn't look exactly like a quadratic problem. However, note that if you just square both sides, you get the quadratic problem back, and you haven't actually transformed or changed anything. Now, when you square the square root of x squared plus 4x and you square 0, note that squaring the square root of something, you actually get plus or minus x squared plus 4x back equals 0. But you can then divide both sides by the plus or minus to get x squared plus 4x equals plus or minus 0. But plus or minus 0 is just 0. So you don't actually, in this case, have to worry about the plus or minus in that case. So we've squared both sides, and we have x squared plus 4x equals 0. Now what we can do is we can proceed to factor the problem as we would in any other case. We can factor an x out. We have x times x plus 4 equals 0. Well, that clearly holds when x is 0, because if you have a 0 here, it doesn't matter that you have 0 plus 4. 0 times 4 is 0. It also holds when x is negative 4, because the term x plus 4 is 0 when x equals negative 4. And so these are the two answers, the two roots of that particular quadratic. Okay, so we've gone through some examples dealing with linear functions, solving for roots of quadratic functions. And now what we're going to do is we're going to consider what it takes necessarily to combine functions. We're going to think about some more complex functions that are composite functions. So combining functions, let's assume f and g are themselves functions that are different from each other. There are two rules. There's a sum rule. F plus g times x is going to be f of x plus g of x. This is just two equivalent notations to write this. And there's a product rule, f dot g of x equals f of x times g of x. So you can multiply functions together and you can add them together. You can also compose them. This involves putting one function inside of another. So this open circle means compose g with f, which means every time you see x and f of x, plug in g. So basically, if you have f of x and g of x, every time you see an x and f of x, you plug in the entire expression for g of x. We're going to go through some examples where we show what we mean by this. That is a composite function. So what we're going to do is derive the following for these two functions I give you. So we have two functions. We have f of x equals 2x minus 1. G of x is 2x squared plus 3x. What I'd like you to do is take the time to derive f dot gx and f composed gx. And so go ahead and take your time doing this. If you need to pause the video, go ahead and do so. Okay. So let's start with part A. We have f dot gx. And what this says is this says multiply. And the key to keep track of everything here is to use your parentheses where you need them. So f of x is the entire expression, 2x minus 1. And g of x is the entire expression, 2x squared plus 3x. So when we're multiplying together, that's all we're doing. Now, if we wish, we can perhaps expand this out more, but we need not do that. We don't need to expand this. You were asked only to multiply the two functions together. You don't need to expand this out into a single expression without parentheticals. Now, f circle or f composed gx, this is equivalent to f of g of x. So basically, every time I see an x and f, I want to plug in this entire expression. So I see in f, I see an x once next to this 2. So that means I want to plug in g of x next to that 2 and still subtract 1. Well, when I do that, I get f of g of x is 2 times g of x minus 1. And then here's your expression for g of x. It's 2x squared plus 3x. So f of g of x is 2 times 2x squared plus 3x minus 1. And that, again, is your answer. Okay, I'm going to clear this off. Now that we've composed functions, we can perform other operations as well. They are not necessarily dependent on being able to compose functions, but one thing that's going to come in very useful, especially in the next lecture, is understanding what the inverse of a function is. So let's define a specific property of a function that allows us to compute its inverse. So a function is said to be 1-to-1 if for all numbers a and b, this condition, f of a equals f of b, implies that a equals b. So basically what this says is if the outputs of two separate numbers, a and b, are the same, then a equals b if that function is indeed 1-to-1. The inverse, f to the negative 1, exists if and only if the function itself is 1-to-1. And the inverse is such that if you compose the original function and the inverse together, you get back the argument x. And it doesn't matter what order you do it in. So the inverse composed with f is x, and the original function composed with the inverse here on the right is also x. Further, the domain of the inverse is just the range of the original function, and vice versa. So you just flip the sets. The range of the inverse is the domain of the original function. As with the test as to whether or not a function or an assignment is a function, there's the vertical line test. Whether or not a function itself has an inverse can be tested in the unidimensional sense using the horizontal line test. If f passes the horizontal line test, then it's going to be said to have an inverse. And a function passes the horizontal line test if you can draw a horizontal line through it and never cross the graph of the function more than once. So x squared, every time except at 0 in this case, when you draw a horizontal line through the function, you're actually passing through the function twice. You're passing here and here, so it's going to fail the test. No inverse. Meanwhile, the square root of x has as its domain starting point 0, and every time you draw a horizontal line through the square root of x function, it's passing through only one point. So the square root of x has an inverse. Okay. Indeed, the inverse of the square root of x is x squared. Oh no, excuse me. Okay. State whether or not the following functions have an inverse, and if so, derive it. So f of x equals 2x plus 3, and f of x equals x squared plus 2. So go ahead and state whether they have an inverse, and if so, derive it. So the interesting thing about f of x equals square root of x is that it passes the horizontal line test, and the inverse of this function is actually x squared. But didn't we just say that x squared fails the test, and it itself does not have an inverse? So we have a contradiction. Well, the domain of root x is what? It's 0 to infinity. Okay? What's the range of root x? The range of root x is also 0 to infinity. So its inverse is restricted to the positive line. So the domain of the inverse is also 0 to infinity. And if we come over here in this picture over here to the left, and we look only at values of x squared in this quadrant, then, and we ignore all of this to the left, which is essentially what this says when we're restricting this domain to 0 to infinity, due to the rule where the domain of the original function is the range of its inverse, etc. Then now notice that x squared actually does pass the horizontal line test on the restricted domain. And that's why root x has an inverse. It has to do with the fact that we have to remember what the domain and range of the original function are, and then ensure that we assign that similar domain and range to the inverse itself. So we need to flip the domain and range and assign it back to the inverse candidate. And that's what we've done. And that's why x squared with a restricted domain actually does have an inverse, and it's root x. Okay, let's do some examples. Again, pause the video if you'd like to do these on your own, and then we can pick back up when you're ready. So we have two examples, f of x equals 2x plus 3. Go ahead and find the inverse if one exists. And the same with f of x equals x squared plus 2. Find the inverse if one exists. If one does not exist, state why. Okay, continuing to finish up. So f of x equals 2x plus 3. What I'm first going to do is, and this is a procedure for finding the inverse of a function, is we're going to set f of x equals y to get y equals 2x plus 3. I then want to find a candidate function such that I can isolate x and get an assignment x as a function of y. And what we're going to do is we're going to then check if this is actually a function at the end. So we're going to find a candidate assignment by resolving this particular object so that x is isolated on one side. So to do that, I'm going to subtract 3 from both sides of this thing here. Divide by 2, I get x of y equals y minus 3 over 2. So is this thing a function? Well, yes. Why? Any y that we plug in, we get back only one x. Notice if I plug in any y, I get one output. So single output per input. And that means that the assignment is a function. So if it's a function, then we know that this is actually an inverse. So now flip the x and y, and we can define the new function as y equals f negative 1 of x. So that is our inverse. And after we have done that, we can now denote that as f negative 1x equals x minus 3 over 2. So that is the inverse of f of x. So the procedure here is to find a candidate assignment by isolating the independent variable as a function of the dependent one. Assess whether or not this object is actually a function. If it is, then the inverse exists. Then you flip your x and y just in terms of notational assignment. You define your new function y equals f to the negative 1 of x, and that is your inverse. You can test if this is indeed the inverse of the function by plugging f back into f negative 1 and computing the composition f negative 1 of f and ensuring that it equals x. And if you do that, you will find that it does indeed equal x. So you would have 2x plus 3, which comes right here. That's your f, minus 3 over 2. You get 2x over 2. These 3's cancel, and indeed you get back x. Okay, last but not least, b, f of x equals x squared plus 2. Again, set y equals x squared plus 2. X squared equals y minus 2. We're trying to isolate the x. We're going to take the square root of both sides. But in doing that, notice that x could be either positive or negative, because x squared, if you have a negative 1, you get the same number as if you put in a positive 1 to x squared. So we do need to consider the plus or minus. We can do is we can move this plus or minus over and divide both sides by the plus or minus, and that means x equals plus or minus square root of y minus 2. Our candidate assignment is then f negative 1 of x equals plus or minus square root of x minus 2. But look what happens. Any x greater than 2, so 2 you get a 0. For example, x equals 3, you get either f negative 1 of 3 is 1 or f negative 1 of 3 is negative 1. And that means that there are multiple outputs per input. So multiple outputs per input possibly. And so f negative 1 is not a function, and then this inverse does not exist. If the candidate assignment is not a function, the inverse does not exist. So that should be noted here. If the candidate assignment is not a function, then the inverse does not exist.